पेपर टेप होगा वहाँ, पेपर टेप होगा वहाँ पे। यहाँ पे आना
इसका
हेलो माइक चेक, हेलो माइक चेक।
हेलो। चेक करना एक बार चल रहा है।
Okay, shall we start? Okay, well, good afternoon and welcome to this fourth A.K. Sundaram Memorial Lecture. Of course, A.K. Sundaram doesn't need any introduction in this institute, but many of you are new here, so I'll say a few words about him before we start the lecture. He was one of the founder members of this institute. In fact, he was one of those group of 7 people who really started this whole endeavor in PRL. And they were invited by Dr. Vikram Sarabhai to do so, because he wanted to start a fusion program in India. So Sundaram was part of that team, and in those initial years, he helped a great deal in formulating the research plans of the institute, and also in recruiting young people and training them. So that was a key contribution that he made during the early days in PRL. And then when we moved here to this new campus, he was the first dean of the Institute for Plasma Research. And in fact, he formulated and structured this entire administration of the institute. And he also ran it successfully for many years before he retired. He was also a very distinguished and eminent plasma physicist, a theoretician, who had a very rigorous training in applied mathematics. So all his theoretical calculations were very precise and meticulously done. He had very broad interests in many areas of plasma physics, in fluid dynamics, in magnetic reconnection, also in basic plasma theory, and applications in fusion as well as in space plasmas. So a very versatile scientist, and it was a great pleasure to work with him. He was a very close friend and a colleague with whom I enjoyed working for many, many years. Our offices used to be right next door to each other. So it was a great pleasure to be with him all the time. In '93, after he retired, he went to NASA and continued to work there for a number of years, particularly worked in the area of magnetosphere, and he made many important contributions there. But as you always like to say, his heart was always in IPR, where he had spent so many years developing and growing up this place. So to honor his memory, this lecture series has been founded, thanks to the funds donated by his family. And today we are very fortunate to have members of his family here. So let me welcome his daughter, Dr. Vidya Sundaram, and his son-in-law, Mr. Bhamitapati. We are also very fortunate in having a very distinguished speaker for today's lecture in the person of Professor Bhattacharya here, Archana Bhattacharya. And I will not formally introduce her yet, but let me say a few personal words about her. I've known Archana for many, many years. We have a very fond association, right from the days when she started her career in IIG in the Colaba campus. I used to visit there often. And also I've known her work, and later on, also when we moved to the new campus, when she was the director of the institute. So it's been a very sweet association, and I'm so very happy that she agreed to deliver this lecture, because her work in the ionosphere and space physics matches very well with Sundaram's own interest in space physics. So very grateful to you, Archana, for coming here. So before I hand over the mic to Paritosh, 2 more requests. One is to ask Vidya to say a few words on this occasion.
Good afternoon. It's such a delight to be here today. I'm Vidya Sundaram. I'm a physician endocrinologist, and this lecture was originally slated for the usual Plasma Science Society conference, kind of put out of schedule because we're here this week and not next week, which would have been ideal. Obviously, Dr. Sen has gone over everything that my dad did and their long association, and I have really nothing more to add to that. We wanted this lecture as a means of giving back to India. When excuse me. So he passed away in April of 2021, and our friend suggested this would be a good way to honor his memory, to either sponsor a scholarship or some sort of thing like that. And we talked it over, and and we had hit on a great idea that we could do something like a symposium. And I loved it. You know, whenever you go to conferences in the US, you always have these huge a symposium lecture, and it's usually some great scientist's name. And I love the thought that I could create something like that in my dad's name. So here we are. So we will keep this going as long as we can. And I want this to be a lecture useful to all of you in terms of hearing great speakers as a way of learning what you can and inspiring your research going forwards. So have a good time. I really thank Dr. Archana Bhattacharya for giving this lecture today. We're honored to have her here. And that's that's my contribution for this afternoon. Thank you.
Thank you, Vidya, and we are all grateful to the Sundaram family for establishing this series of lectures. As you know, this lecture is actually organized by the Plasma Science Society of India, and I would like to convey our thanks to the society, particularly to Paritosh, for all the hard work he does. Over the years, he's always organized this effort. So thank you so much, Paritosh. Now, I'd like to request Paritosh now to formally introduce our speaker today and invite her to give the talk.
Thank you, Professor Sen. It's a great honor for me to introduce such an eminent scientist, Professor Archana Bhattacharya. She is INSA scientist, INSA honorary scientist and former director of IIG Mumbai. And after completing her BSc and MSc in physics from University of Delhi, she received a PhD degree from Northwestern University, USA in 1975, working in the area of theoretical condensed matter physics. She returned to India and joined the Institute of Geomagnetism. In 1978, she was introduced to the topic of ionospheric scintillations in 1980, when she started working with the first digital data of scintillations recorded in India on radio signal transmitted from the NASA satellite ATS-6. At that time, there was no theoretical work being done in India in this area. So she started working on the theoretical aspect of scintillation along with analysis of data. Yeah, निशा 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 आपका स्पीक ये ऑन म्यूट कीजिए आपका. That is the problem of online. Since it is online, most of them are just attending from their desktop. Instead of coming here, Okay, let me continue this. During 1986-87, she worked on the theory of strong scintillations to better utilize the data with Professor Casey Young's group in University of Illinois Illinois at Urbana-Champaign in USA. Interest in this area was received when the Global Positioning System GPS constellation and became operational in 1993. She was the National Research Council Scientist, Resident Research Associate in the Air Force Research Laboratory in USA during 1998 to 2000. She was appointed as the director of IIG in 2005 and served in that position until 2010. After that, she was continued to work in IIG as a J.C. Bose National Fellow, Senior Scientist with 2 years of IIT Bombay, and currently as an INSA Honorary Scientist. Her recent work has been concerned with the spatio-temporal evolution of electron density irregularities in equatorial ionosphere, which is of particular interest in the region of low geomagnetic latitudes such as India. So her research interests are plasma instabilities in the equatorial ionosphere, probing the ionosphere with radio waves, effect of space weather on the ionosphere, spatio-temporal variations of the geomagnetic field. I'm just telling these research interests particularly to the research students. Now I request Professor Bhattacharya to deliver a talk.
Can you check that online audience able to hear or not?
Yes, that I'll check.
No, after doing this.
No. We have not done anything. We have just reduced the speaker.
Yeah, first of all, I'd like to thank the Sundaram family for having this series of lectures. I'd like to thank Professor Sen for inviting me to give this talk, and PSSI also. And I would like to thank Dr. Paritosh Chaudhary for his very nice introduction. It's a great honor for me to give this lecture. And, I had not had the opportunity to personally meet Dr. Sundaram, but I was aware of his work because, he had made very important contributions which were to, microspheric physics, which were very relevant to geomagnetism. He had worked on the tearing mode instability in the plasma sheet. He had proposed a mechanism for magnetic reconnection which would trigger substorms. These phenomena actually make changes in the ionosphere too. So this is of great importance, to us who work in the field of ionosphere and geomagnetism. And then, Dr. Sundaram also worked in the high latitude ionospheric instabilities. In the high latitudes, those are mainly driven by field aligned currents and the high electric fields that are present there. Because of the geometry of the Earth's magnetic field, these are the important sources of instability in the high latitude ionosphere. I will be talking about one particular instability in the equatorial and low latitude ionosphere, because the two regions which are most vulnerable to instabilities are actually the high latitude region and the equatorial and low latitude region, when India, of course, falls in the equatorial. This is the magnetic equatorial, and low latitude region. Most of India, the low latitude ionosphere is over India. So these things are of use to us. Now, I'll start with the large-scale structure of Earth's ionosphere, and then come to the observation of irregularities. There are various techniques. There are a number of radio techniques and optical also, which are there to detect these inhomogeneities on different spatial scales. And then, of course, I'll talk about some of the theoretical aspects of the development of equatorial plasma bubbles. Because, in this field, observations and computer simulations of the Plasma Institute have gone hand in hand. I'll show you where, because it's a very complex system, as you will realize. And nature, is something we can't control. The conditions are presented by nature. So things get complicated. But I'll talk about some of the theoretical aspects, and then I'll talk about ionospheric scintillations and how ionospheric scintillations are used to extract information about the irregularity characteristics by relating the parameters that we obtain from scintillation data with the irregularity characteristics. Finally, I'll summarize some of the insights that we have got from scintillation observations regarding the development of this particular plasma instability. Now, we of course live in a connected system. The sun and earth are very well connected, not only through the electromagnetic radiation that we get from the sun, but also through the particles that come from the sun. And so solar variability is very important for Earth's ionosphere. It has a huge impact on Earth's ionosphere, not only because solar extreme ultraviolet radiation exchange partly ionize Earth's upper atmosphere, particularly the equatorial low latitude regions, but also because the Earth-directed coronal mass ejecta and high-speed solar wind streams, which come from coronal holes in the higher latitudes of the sun, and they carry with them the heliospheric magnetic field. And when the orientation of this magnetic field is right to reconnect with Earth's magnetic field, which in this figure is pointing northwards, so a southward heliospheric magnetic field, or what we call as the interplanetary magnetic field, when there is a southward component to it, then reconnection takes place and magnetic storms occur. Okay, so solar variability is sort of key to the state of the ionosphere. Now the vertical structure of the ionosphere comes about because as the solar radiation comes towards the Earth, its intensity decreases because it has been interacting with atoms and molecules that are present in the upper atmosphere. And then it's also at the same time meeting increasing densities of neutral particles as it comes down, because the neutral atmosphere is hydrostatic equilibrium. So you have the heavier species at the lower heights, particularly above 100 kilometers, where the different constituents are no longer mixed together. They separate out according to their masses. So the heavier molecules are present at the lower heights, and the upper reaches, it's the atomic species. For us, the region of importance is the F region of the ionosphere, where atomic oxygen prevails, and so the major ionic component is O+. And the different layers come because of different constituents in the upper atmosphere, basically. Now, of course, recombination is also something which takes place all the time. But post-sunset, that becomes very important. So, and the molecular components, molecular ions recombine at a much more rapid rate than the atomic species because of energy considerations. So the D region practically disappears. The E region, plasma density is much reduced, but it doesn't disappear, which is important for plasma bubble evolution. And, of course, F region densities are also less, but there is a steep upper density gradient at the bottom of the F region, as you can see here. Now, one thing to be noted is that there are still a very, very large number of neutrons in the upper atmosphere in the ionospheric region. This is referred to as the thermosphere. And, electrons, the gyro frequency is much higher than the electron collision frequency. So electrons tend to be magnetized in the E region as well as the F region. Ions, on the other hand, are not magnetized in the lower reaches, E region. But F region, the effect of neutrons starts decreasing and decreases quite rapidly as you go up in height. Nevertheless, ion-neutral collisions are still very important, and they compete with the magnetic field in controlling the dynamics of the ionospheric plasma. Now, apart from the vertical structure, there's also latitudinal structure of the ionosphere to be considered, and this comes about because there are tides in the atmosphere due to solar heating and lunar gravitational pull, which give rise to neutral winds. And these neutral winds, because the ions collide with the neutrals, tend to carry the ions with them to some extent. And electrons, of course, are not influenced by the collisions with neutrals. So there is current which can flow. So F region also has a Pedersen conductivity, but the Hall conductivity is released because these neutrals give rise to the neutral wind is associated with an electric field, basically, which is eastward during daytime, and that causes in the F region both electrons and ions to drift together almost with an E cross B drift, which is vertical. And once they start rising, they also tend to diffuse along the field lines very easily due to gravity and pressure gradients. And so what happens is there are these two off-equatorial regions in the low latitude ionosphere where you find very high density. These are called equatorial ionization anomalies, and they also play a role in scintillations and so on. So pointed this out. Now, to observe the irregularities, some of the radio techniques are ionosonic, where you actually send up a signal, you sweep this radio signal through a range, and this goes up, comes down, reflected from a height where its frequency equals the plasma frequency. And once the group velocity becomes zero, of course, it takes infinite time for the signal to come back, and that's what you get here. So this is how you get information about the different layers of the ionosphere, because what you get here is virtual height, because you're assuming from the time taken by the signal to return and multiplying the velocity of light, you get the height, which is virtual because it's not really moving with the speed of light, but with a lower speed. Now, in the presence of irregularities, you don't get such a clean picture, you get spread, and this is something which was seen way back in the 1930s, and that is from where they started calling it spread F. And because it was observed mostly on the bottom side of the layer, Dungy in 1956 proposed that there must be, due to a collision-dominated radial instability occurring on the bottom side of the F region, where, as we have seen post-sunset, there is a steep upward density gradient. Now, in the 1960s, the incoherent backscatter radar was set up in Jicamarca in Peru, which is again very close to the magnetic equator. And there they started observing very strong signals, which was due to coherent scattering from irregularities. And these were definitely going above the peak of the F region, where the density gradient is downward. So Dungy's theory was put aside, and it was not until 1976 there was a breakthrough with Scanapiecho and Osako simulating the nonlinear development of the radial to show that this low-density region could actually rise up and go to the top side, okay, which is linearly stable. I have shown here some range time intensity maps from our MST radar, which is located at Gananki. This is run by the National Atmospheric Research Lab. And this is ideal for seeing how much the plasma bubble structure varies from one day to another. Although, this is Bragg scattering, so for a 53 megahertz radar such as this one, the scattering is caused by nearly 3-meter scale irregularities, and we come to what produces these versus the plasma bubble. Of course, there is, plenty of satellites and rockets have made measurements. So I'm showing here two satellite observations. One by a satellite which was put up by the Air Force, US Air Force, just for, forecasting communication navigation outage called CNOPS. And, plenty of plasma bubbles were observed with this. And they also measured the plasma drifts, ion drifts, and came up with this meridional and zonal drifts, which were, of course, due to electric fields perpendicular to those. And those are also shown. So you can see that the plasma bubbles are also related to, electric field fluctuations, both in the zonal and meridional direction. And then, in the 90s, at least 2 satellites had observed magnetic field fluctuations associated with plasma bubbles, but these are very few. And also these all, localized objects. Although I see recent uh, radiation which comes when oxygen ions recombine, and this recombination leads to actually an excited atomic oxygen, which when it gets back to the ground state emits this radiation, and its intensity is proportional to, is indicative of the peak plasma density. So where you see these dark patches, these are actually plasma depletions. So this is a picture where you can see that in the South American region, the dip, this is the dashed line is the dip equator, and it's at an angle to the geographic equator, and of course these plasma bubbles are along the field lines, highly elongated along the field lines, and not only that, you can see that they cover a very large longitude range. So there are times when you can have plasma bubbles over a very large region. Now, before I come to the theoretical aspects of this, I would like to just point out that in the F region, the parallel conductivity is, of course, much higher than the Pedersen conductivity. And Hall conductivity is nearly 0 because electrons and ions are both moving together closely. And above an altitude of 130 kilometers, the ratio of direct to Pedersen conductivity is 10⁴. So in many instances, the geometric field lines are considered to be equipotentials. Okay? That is one thing which is made use of has been made use extensively in the theoretical developments. And the other thing that I want to point out, as I said, the E region does not really disappear, but because of the high conductivity there, the Pedersen conductivity in the E region at night time can be quite large. It's very significant, so it should not be neglected, and it plays a role. Now, the basic idea of the Rayleigh-Taylor instability, which most people here would know, is of course that you have this upward density gradient, and the gravitational current, because gravity acts loosely on the ions, and the gravitational current is divergent where if there is a perturbation like this, setting up charges and an electric field, which makes this low density region rise up. Now, of course, so that is how it rises and then goes to the top side nonlinearly and develops structure also. Now, I should point out, as one said, it's not only gravity, but if you have a Pedersen current, so if there's a background electric field, the Pedersen current would also be discontinuous at these edges, and that also contributes, but the contribution of gravity is much more than that due to the electric field in the F region. And it's a post-sunset phenomena because these electric fields, perturbation electric fields, are mapped along the geometric field lines, which are, if you're assuming equipotentials, they just map along the field lines to the E regions at the two ends of the magnetic field line. And the E regions can be highly conducting still. Certainly during daytime, they are so highly conducting that they discharge the bubble immediately, and the plasma bubble does not grow during daytime. It's a nighttime phenomena. And as we will see, even after sunset, you have to keep in mind that this connection has to be there and it can play a role. So what happened is, because of this mapping of the field lines, along the field lines and all, Herendel in an unpublished report, he said you can just use field line integrated quantities instead of taking a full three-dimensional picture of the ionosphere. You do a two-dimensional cut in the equatorial plane, and then you can, naturally simulation becomes a lot easier. And, so most of the simulations done until fairly recently were two-dimensional, using field line integrated conductivities, and everything is integrated along the field lines. And you can see that structure develops here. Only thing is, the problem with simulating this, you have to have a realistic background, because as you will see that the ionosphere, as I said, during daytime there is an eastward electric field, and that eastward electric field becomes westward at night in the ionosphere, the ambient electric field. But before reversing, it sort of gets enhanced because of the conductivity gradients that are there across the sunset terminator, and mapping of the field line and so on. So this causes so-called pre-enhancement reversal, which is very important. Because of the presence of collisions, if you look at a linear theory, you will realize that the higher the F region, greater the chances, greater is the growth rate, because ion neutral collision frequencies are less. In fact, the lower side, bottom side is a collisional instability maybe, but as you go, you have to think of collision less. And also, other thing that is neglected here totally is thermospheric winds and things like that. So, in a realistic simulation, you have to consider the background, changing background conditions, which becomes quite problematic. And, so this, as I said, the coupling of the E and F region through the geometric field lines is critical for the development of the equatorial plasma bubbles. And, we took a simple picture for basically a transmission line picture of the F region generator connected to the E regions at both ends in the northern and southern hemisphere. And, this was already suggested by one of the previous Axon when he observed magnetic field fluctuations in G2, that maybe alpha waves are the carriers of the field line currents. So, we looked at the possibility of shear alpha waves being generated when a plasma bubble starts to grow in the equatorial F region, and then these field aligned currents couple the equatorial E region with the F region. And, in order for the bubble to grow, the condition is that, both the E regions should go to have the same conductivity, which is very, very low, so going to 0. So simultaneous sunset at both ends of a geomagnetic field line is something that is required, which was actually seen also in this, occurrence rate of plasma bubbles obtained from satellite observations of the plasma bubbles. And this is at an altitude of 840 kilometers. Now the thing is, in the Indian region, you see very little, partly because the magnetic field strength in the Indian region is much higher than in the South Atlantic region. As you probably know that the South Atlantic region has the lowest strength of the magnetic field globally. And so the plasma bubbles can really rise up in E cross B drift, delta E, the perturbation electric field of the relative instability can make it rise up much higher than in the Indian region. And also the growth rates are higher. So you see a lot more. But the important thing is that this is the magnetic field aligned, the terminator and the time of the year when the magnetic field lines are aligned with the sunset terminator. And because the angle between the geometric field and the geographic north, geometric north and geographic north is the declination, is very high in this region, Because of that, there is a real deviation in the seasonal distribution of plasma bubbles. This is something which was also suggested by Sonoda way back in 1985, but just considering low latitude occurrence pattern of scintillations at different longitudes along the globe at the equatorial locations. So basically, the transition line actually says that both have to go to the sunset has to happen simultaneously at both E regions at the end of the magnetic field lines, which was not something which the simulations specifically said. And so the next thing is how low should the E region conductivity be in order for the instability to really go into a chaotic state. Now for that, we found this condition. So in this, a new time scale was introduced by the, you have the E region resistivity, conductivity, and you have the capacitance of this F region, where you have the charges are accumulating. And, so that time scale for discharging the bubble through the E region is given here. And that means it is a more stringent condition for the growth of the plasma bubble. Now, of course, a magnetic field, electromagnetic version of the relative instability requires a 3D modeling of the development of EPBs, which was done by Aman Basu in 2005 and the Cornell group in 2013. Both found, of course, the magnetic field fluctuations to be small, which they are. For Basu and all, they did a linear calculation, but then they did with normal mode calculation for the magnetic field and electric field perturbation calculations. Dow et al. Considered the system under extremely low flux conditions when the growth rate is very low. Because these pre-reversal enhancements that I was saying of the height rise of the base of the F region, that is very solar cycle dependent. The solar cycle, we see very little change in the visible and the infrared that comes from the sun. The total irradiance of the sun, that is dominated by the visible, and that changes by 0.01% during the whole solar cycle of roughly 11 years. But the ultraviolet and X-rays can change dramatically. the extreme ultraviolet can change by as much as 100%. So for the ionosphere, these changes are very dramatic, and during high solar flux, high sunspot years, when the solar flux is much higher in these wavelength ranges, you have very high increase in the pre-reversal enhancement, and also the growth is more rapid. But to keep the growth small, basically the reason they consider only very short-term scale, time scale for determining the development of the bubble through electromagnetic instability was that they wanted to study the dynamics of the alpine waves, going up to the region, some of it getting absorbed there, reflecting back and all. And, so for low magnetic flux, the basically the alpha waves travel faster because the ion mass density is lower. So they could do the simulation for a short time, but in this short time, the plasma bubble didn't grow at all. So anyway, so their thing says that the system becomes electrostatic after 15 seconds because the alpha waves stop they're not there anymore. Whereas the swarm satellite constellations continuing to observe magnetic field fluctuations of the order of 1 nanotesla. So much more simulations need to be done there, but apparently it's very time consuming. Now, coming to the propagation of radio waves in the ionosphere, of course, the refractive index, the signal frequencies that we are considering now is very high frequency, 200 megahertz and above gigahertz and so on. So those are much larger than the plasma frequency and cyclotron frequency, collision frequency, and the refractive index basically becomes a very simple, takes a simple form where n is the plasma density. Now, as you will realize that if you were to integrate find out the time taken, from the time taken by the signal to reach from the GPS satellite to the receiver, if you want to calculate, sorry. If you want to calculate the range, it will be a pseudo range because once again you're assuming it's traveling with the speed of light. But actually, because it's moving slower than the speed of light, there is an additional, it slows down the signal and you get an additional contribution to the range that you get from the satellite. And that depends on the total electron content along the signal path. Okay, so now as you know, in GPS you need to see the ranges, get the ranges from 4 different satellites, and then you obtain the location and any error in time. Now, because of the presence of the ionosphere, you have these errors in positioning. And actually the ionosphere has maximum contribution to the errors in positioning. So actually, a simple model of the ionosphere is there with all GPS software, and that model is due to our friend Jacques Bouchard, and so that offers partial correction for the ionosphere in positioning. Okay, now the errors caused by ionosphere can be as large as about 15 meters, which is not important for an Uber drive, but if you are trying to land an aeroplane using GPS, then it's important because they need vertical accuracy of 1 or 2 meters and a horizontal of 5, 6 meters. So that is why the ionosphere. But more important, this is for a smooth ionosphere. More important for the ionosphere is what it got stuck. You can do the close it and start again. हाँ डेस्कटॉप पे है ना आप बंद करिए डेस्कटॉप पे Yes, you can open this also. You can open this also. Yes. Yes. इधर से नहीं हो रहा okay okay so problems arise when the ionosphere is not homogeneous and there are structures which can scatter the signal and that happens that is what ionospheric scintillation is all about. So you have these plasma waves, the electromagnetic radio signal is coming down. It goes through the plasma layer, and even within the plasma layer, it develops phase and amplitude fluctuations. But just to show you that you can have an emerging wavefront with all these fluctuations, then it propagates through free space from the bottom of the layer to the ground and develops further amplitude and phase scintillations. And those look somewhat like this. And what happens is that for weak amplitude scintillations, maximum contribution comes from the Fresnel scale. This is because, if you consider variation in the phase like this, in the layer, then as it propagates to the ground, you can see that, and this is, the scale length of the waves is much larger than the signal wavelength. The signal wavelength for gigahertz is just a few meters, and so the scale lengths are much longer, and therefore you have maximum, constructive distinct for when you have irregularities of this size. When G is this. This is called the Fresnel scale, and you can see in the spectra also there is a maximum here, which of course what happens is because the irregularities move with respect to the signal path. For a geostationary satellite, because the irregularities tend to drift with something. Either they're drifting with the ambient plasma, or we will see something causes them to drift. There are of course perturbation electric fields associated with the plasma instrument also. So as they drift past, so the pattern of the diffraction pattern, so to speak, on the ground also moves past the receiver, and you see temporal fluctuations of the signal. And this is what is recorded here. These are the phase scintillations, and these are called scintillations, so and amplitude. And because of that, of course, this is a temporal path spectra, which you can convert to a spatial one if you know the drift. Now, to know the drift, you'd like to do space receiver calculation. But before that, let me show you the scintillations on GPS signal, where the scintillations are due to irregularities of about 350 meter scale sizes. And the refractive index, of course, now varies and in the presence of irregularities. And if there are enough irregularities of this scale size, they cause scintillations of the signal. This is actually weak scintillation. You get a much stronger scintillations where the loss is like, many more decibels. And also, because the GPS gives out two signals of different frequencies, and the ionosphere is a dispersive medium, its refractive index depends on the signal frequency. Therefore, you can actually use these two signals, the ranges from these two signals, to derive the total electron content along the signal path. So GPS actually proved to be a real boon for people studying the ionosphere everywhere, even in India. People have receiver, and they're studying the changes in the total electron content. Now, the point is that here is a plot of the total electron content, not exactly, because this also has the effect of phase scintillations, okay? But approximately, this shows you the presence of plasma bubbles, these deep cutouts in the total electron content due to the presence of bubbles and associated diffusion. Now, as I was saying, to convert the temporal variations into, related variations, you need to know the drift of the irregularities past the signal path. And to do that, you want to, you can put up two spaced receivers to receive this signal, and that is the standard method. But, people also realized that the structure of the scintillation was changing with time. So what one started using is space-time correlation function for the scintillations of this form, where this part actually tells you that there can be decorrelation of the signals, okay? And so from space receivable scintillations, actually you can calculate both the average drift of the irregularities and, which is basically, the standard method just tells you that this time lag is caused by the drift, and therefore you can, knowing the separation of the two receivers, you can, but because of the presence of this, it gets a little more complicated. But so this is actual data, autocorrelation, cross-correlation, and this is the nature of the scintillations. Now, so the standard parameters that are calculated from such space receiver experiments is, of course, the S4 index, which measures the strength of the scintillations, which is mainly the standard deviation for normalized intensity, the average drift, this parameter VC, and this is the maximum cross correlation between the two signals. As you can see, only in the initial part there is a very strong decorrelation, as also the velocities and VC and V naught cannot be determined because that method is not very accurate when the cross correlation falls below 0.5. But this repeatedly happened only in the beginning of the scintillation event, so people were puzzled that why is it that, later on things to become smooth, there's a drift which sort of you expect the plasma drift to be like that, the ambient plasma drift to be like that and all. So, we thought that to figure out that, we need to model scintillations using certain space-time characteristics of the irregularities themselves and see if the resultant scintillations have space-time characteristics as described by the Briggs form. So for that, there are two ways of doing that. One is, you sort of compact the whole irregularity layer into a phase-changing screen, single phase-changing screen, and where the phase is, of course, changes are related to the total electron content, changes in the total electron content due to the presence of plasma bubbles and the associated irregularities. And in the plane of the irregularity, you would calculate the complex amplitude, which is an amplitude and a phase. And then you can also calculate the space-time. See, usually we do not know this thing. We do not know this. But we have space-time characteristics of, we can assume some space-time characteristics for this. In situ observations by satellites and rockets have shown that irregularities have a power spectrum, mostly a power loss spectrum, okay? So you know that that aspect is there. But what about the time part, So for that, we found that, Shkerovsky had used this form to describe irregularities which also change with time as they move. And, this kind of space correlation function is quite useful for, analyzing scattering due to turbulent flows. That's what Shkerovsky used it for. So, we thought we can also use it. So, you calculate the space-time properties of the amplitude from this calculation related. So then that will involve this So you will have, using this for the irregularity, this kind of space-time characteristics for the irregularities, where phi k is now the irregularity spectrum, for instance, measured by the satellites, okay? And that is for irregularities which are not changing with time, and to incorporate the changes with time, you put in a sigma. This is due to velocity fluctuations now. If the velocity fluctuates, you can have, the signal also changes. So to do that, so there's a decay in the correlation due to velocity fluctuations, which is what we find in understanding. And the other way of calculating, of course, is to directly, when you have to account for these are thick layers, at least 50 kilometers thick around the F region peak, because scintillations as such is an integrated thing. Maximum weightage comes from the region with the maximum ambient density, delta N is largest there. So you have, but still about 50 kilometers thick irregularity layer is. And within that, also amplitude scintillations develop. That is important. The phase screen does not account for that, so you can do that. And then you actually calculate directly the moments of this complex amplitude. And as you can see, a special case of the fourth moment gives you both the S4 index as well as the space-time correlation function of the intensities. And you can do that, and actually you find that the space-time correlation function that you obtain for the scintillations after doing this calculation does in fact more or less fit into the pattern that we use for analysis of the V0 and VC from scintillation data. That is the BRICS. So you have now a means of relating that parameter VC to some characteristic of the irregularities, and we said that this is actually for weak scintillations and saturated scintillations, VC is exactly equal to sigma V. We can put it in the exact form. But for intermediate things, you have to do a numerical calculation, so hence the approximate. So VC can actually be identified with the Rayleigh-Taylor perturbation electric field. That was our conclusion. And that really solved some puzzles, because earlier, when there were scintillations on a magnetically disturbed day, they were surprised that, the ionoson only showed a height rise of the F layer in the initial times and extended initial time because of the magnetic storm. Magnetic storms change the electric fields in the equatorial ionosphere. And there is also another way, mostly because of closed field lines, as I said, that there is no, the equatorial and low latitude ionospheres are very well protected from all that is happening in the high latitudes of the magnetosphere. But once in a while, the shielding does not work. When it breaks down, you can have a promptly penetrated electric field from the magnetosphere to the equatorial ionosphere. And also there's another mechanism called disturbance dyno, which is basically due to very strong enhancement of currents in the high latitude region, auroral region. The currents are enhanced because electric fields are larger there, and the conductivity is also enhanced because of particle precipitation. And because of this, you can have heating of the thermosphere in that region. Joule heating causes the thermosphere to rise, and then the composition changes, and you can have that come down to the equatorial region. So these are two ways in which the storms can alter that. So, but the thing is that, what is, there is no change in the height, so no electric field perturbation. So what is causing these scintillations to occur? Why are they suddenly growing up? So now we could see that initial part was due to, the height rise and growth of the Rayleigh-Taylor instability. But somehow, this is a problem which is there with ionoson, radar, and scintillation, where you actually are observing what is happening overhead at that particular time. These things are drifting. So even these nice radar pictures, then people realize nice radar pictures are really not what is actually happening. You're not tracking the same bubble. Something else is drifting in, because this drift is eastward ambient plasma drift, even when the perturbation electric field of the Rayleigh-Taylor dies down, these irregularities drift with the ambient plasma drift. So, these scintillations are caused by irregularities which were actually generated maybe thousands of kilometers to the west of the observing point, and then they drifted over the overhead and you observed them. This is a problem both with radar and anosone also. So anyway, after that, a little more attention was paid to the plasma bubble, because I remember asking Joe Huba if he had any calculations of the electric fields to this thing, because John Retterer in Air Force Research Lab had done some, but he never published those results. So Joe Huba actually did, his group, later on 2010. And the DMS-3 satellite also observed these fossilized bubbles where the Rayleigh-Taylor perturbation electric field has gone, and these plasma bubbles, the dead bubbles, are just drifting past. These are there, and you don't have any electric field or velocities associated with this thing. They are just drifting, but they are drifting with the ambient. So then you have this simulation. Now this is 3D simulation, because once again, they have shown here that the plasma bubble actually keeps rising, and that when the perturbation electric field dies down, the plasma bubble doesn't rise anymore. Initially, you have this electrostatic potential, which represents the perturbation electric field due to the Rayleigh-Taylor instability, but that is gone here. It defies the electrostatic potential. So, these things are there. But this is of interest because here, of course, it has gone very high, and they've somehow, it took them a long time to get the plasma bubble to reach this height. But usually it happens much faster. But the important thing is that when the plasma bubble extends into the equatorial ionization anomaly regions, it was expected that strong scintillations will come simply because of the high background electron density. And until recently, that was what was believed. Because, if you look at L-band scintillations on the GPS, GNSS satellite signals, which are all L-band signals, you have strong scintillations, 10-degree geomagnetic latitude onwards, but none in the equatorial region, none. So why is that so? So, because here what you have is at different times, the distribution. This is the large scale. Now, this is the large scale over all of, a good part of India, the spatial and temporal distribution of L-band scintillations. So, to explain that, so because this is a picture of what happens, we did an experiment where we also had VHF receivers receiving 251 megahertz signals from another satellite, and that had very strong scintillations in the equatorial region, very weak L-band scintillations. Here also strong and weak because it is frequency dependent. So at a given location, you expect the higher frequency signal to show weaker scintillations, but the relationship between these two here and these two here is very different. So, to explain that, we actually model the scintillations, again calculation of the fourth moment equation, but now with different spectra for the irregularities. And we saw that if you have a very shallow irregularity spectrum, then what happens is that the signals are basically focused by these large irregularities. And this focusing causes large scintillation variations on the ground, and you can get S4 exceeding 1. That happens. But if the irregularity spectrum is shallow, presence of smaller scale irregularities scatters the signals, so this focusing is lost. So for shallow irregularity spectra, the saturation, as you increase the strength of the scintillations, they'll simply saturate. But whereas for steep irregularity spectra, you can have focusing, and that can. So in the equatorial region, you have focusing of the 251 megahertz signal, because this is all wavelength depending, the Fresnel scale depends on the signal wavelength. So for the L band, it is different though. For L band, unless this irregularity spectrum is shallow, you just don't have the 300-meter scale irregularities. So no matter how much you increase the strength of the irregularities, L-band scintillation does not increase. Whereas you have to have a shallow spectrum in order to increase the L-band scintillation. So this is how we explain the presence of strong, that you have to have different irregularity production in different regions, so that the irregularity spectrum at different heights over the equator is different. At the top, on the top side, the bubble is much more structured than near the F region peak. As I said, the maximum contribution comes from the F region peak because the background ambient density is highest there. Top side, the background density is so low, delta n, there will not contribute to equatorial scintillations, but these are mapped along the field lines to off equatorial latitudes, particularly near the equatorial ionization crest where the background density is higher. So then they make map, and then they can cause, only if this smaller scale structures prevail on the top side, that can go mapped to the off equatorial location and produce the strong scintillations. So the importance is not so much of the ambient density. You first have to have this kind of structuring of the equatorial plasma bubble. And again, you need three-dimensional this thing, which is going on, particularly this Japanese group. But they also get, because so much time is required, they also get very little time, it seems, on their huge computer. But you can see that once this is here the equatorial F region peak. Here where the plasma is rising, it is not so structured, but on the top side it is structured, which maps down to the F region of at 400 kilometers away from the equator and produces strong scintillations. But the required resolution is not yet reached. And coming to the last one is, as I said, the role of the thermosphere in EPB evolution has not really been studied. So to see that, we have to pick 2 days with identical ionospheric conditions, which we did. The height rise is about the same. See, this is the time when the electric field, ambient electric field in the E region reverses, the ionosphere comes down, so it's happening around the same time. And if the total electron content also shows the presence of the equatorial ionization both the days, and there is very little difference in the total electron content on these days. But the 2 days show very different latitudinal structure. In the second day, which was after a major magnetic storm of 17th April, there was very little, the extension was just not as much as on the other day, which was on a quiet day, undisturbed ionosphere. So, and this is not because the structures was not, in this case, even the plasma bubble was missing because VHF scintillations also did not extend as much as they did on the 13th. 20th, which was after the magnetic storm, they were curtailed. The latitudinal extent was curtailed. So to explain that, we needed some thermospheric data. The thermosphere, the problem is there isn't really much data. Neutral observations are very much more difficult, very few observations. So modeling. So Tim Fuller-Rowell in National Center for Atmospheric, he helped actually. So his group did the thermospheric modeling for us, and we found the atomic extinction is much higher after the magnetic storm on the 20th of March, whereas 13th March is lower. So, because of the lower ion-neutral collision frequencies, the plasma bubble initial rise velocity is much higher on the 13th. So it went up faster, this went up slower. At the same time, what usually is not modeled, that the background ionosphere is coming down, okay? Now, Huba's group had shown that very important question is, when do the plasma bubbles stop rising? Because that is very important for determining the latitudinal extent of the scintillations. So they said, okay, when the ion density is outside and it's maybe field line integrated, become equal to the density inside. So that is going to happen on the 20th of March, much earlier, because it's rising up slowly, but ionosphere started coming down, so that condition is met at a lower height, and therefore the latitudinal extent was much less. So these are basically the summary of some of the insights we got into plasma bubble development by modeling scintillations and comparing with observations. And one, of course, is the distinction between scintillations produced by nascent and fossil bubbles. And the other was, why do we have strong L-band scintillations in equatorial ionization anomaly region? Because the background density is not always that much higher than what it is in the equatorial region. So it's the irregularity spectrum which makes a difference. How the irregularity spectrum develops at different heights within the plasma bubble. And thirdly, of course, the thermospheric conditions, what it does to the evolution of the plasma bubbles, its height rise and so on. So the extent of the latitudinal extent of the scintillations determined by that. So basically, these are some of the things that we got from the scintillation observations about the EPB development. Thank you for your attention. Yeah, as I said, in this region, E region E cross B is important, because there are no density gradients in it. Here, because the steep density gradient and the electric fields are relatively weaker. In the high latitudes, what I was saying, the electric fields can become very strong during a storm, because the field lines, after reconnection, some of the field lines open up. That happens in the high latitudes. So you can have the Swalavian electric field mapped down to high latitude. So the E cross B becomes much more important in the high latitudes.
At the same time, after the reconnection, you have magnetic field gradients also, and you have a large curvature also.
Yeah, here the curvature again is not so important because, but the curvature is there, but it's not, not so important. So most important, gravity, as I said, even the Pedersen current due to the ambient electric field, it is included in the simulations because people usually use an ambient electric field. So that is, but that contribution is smaller than the branching figure.
Thank you.
I have question related to E cross B drift and again role of gravity. It looks to me that when electric field is stronger, then E cross B drift basically moving up or down, and then whatever density gradient was established because of gravity, that density gradient again get enhanced. Means this perturbation grows. Is it so?
See, one is of course the perturbation electric field of the instability itself.
Yes.
Which is actually stronger because that gives rise to very large, these plasma bubbles, they go up at 100 meters per second or higher. Whereas normally the ambient electric field is millivolts per meter. So then, the normal vertical drift is not so high. It may be 20 meters per second or something.
Okay. Then what is the role of Pedersen current? Because Pedersen current in the direction of electric field, and then that can means short circuit the charge separation. Is it so?
So Pedersen current, as I said, that will also have, it will be divergent. If there is a perturbation on the bottom side, so it contributes. As I said, here I didn't show, but actually the Pedersen conductive, the E region, the ambient electric field is always included in all the calculations. It comes together with the, in fact, I showed in the last slide I included the ambient electric field also for the velocity rise.
Yes, this velocity, GY.
Yeah, yeah. So that is the form how ambient electric field comes in. And if you calculate the two terms for normal electric fields, and actually once the background electric field becomes westward, then it's stabilizing. See the E0, what I was telling you that time, it varies with time. The ambient electric field in the ionosphere, it is eastward during daytime, that extends a little after sunset because of the post reversal enhancement, and then the electric field reverses, the ionosphere starts coming down. And if you have a westward electric field, that is stabilizing for the volatile instability.
Okay.
And it will also not help the bubble go up. I mean, it will reduce its upward drift also.
Okay, I have my last question.
Yeah.
See, I don't know what happened during satellite launch because our satellite is mostly in the equatorial zone. Then, logic, whatever I understand, there should be different observatory long distance away. Not only one single observatory, 2-3 observatory normally present. Is it because of this scintillation irregularities can pose problem for one observatory and then not for the second one?
Actually, already in India they're flying aircraft using this Gagan system. It is geo-aided and GPS-enabled navigation. India has its own regional satellite system. Right now, GNS, GNSS.
Yes.
After GPS, you have the European Galileo, the Russian GLONASS, the Chinese Beidou, and India's this thing is regional. The other ones have many satellites, like GPS is 24 satellites going out in orbits throughout the globe, okay, covering the whole globe. But other satellites are also there. But the Indian satellites cover our region. There are 3 geostationary satellites and 4 geosynchronous. So geosynchronous.
Those are not very high altitude, right? Geostationary.
Geostationary is 6 Earth radii, and geosynchronous also same, but it's not in the equatorial plains. So, but those are there so that when an aircraft flies, it can get updated ionospheric models from the station. So these are all for also updating.
Aircraft is only 10 kilometers or so. Aircraft, you are telling aircraft means not with civil aircraft, but something different?
The aircraft flows at a much lower, but the GPS, its position is also determined by the GPS or GNSS. So signal is passing through the ionosphere. Aircraft may be flying there. So it's
okay. Aircraft itself is getting the signal.
Aircraft still has to worry about ionosphere. So people are working on this real-time ionospheric models which will be upgraded. But the problem is, scintillation has showed, sometimes in one launch, you'll have and that too, I showed only the signal parts which are, which have an elevation angle greater than 55 degrees. You can have many satellites, some very low, but low ones are really inaccurate because they bounce off many other things also. Okay? So you have to, in general, if you want to get information, you should look at higher satellites, which does not always happen. So that can also be. But because scintillations, the plasma bubbles are feeling like you can see so much. So what happens if all satellites are, all signals are compromised? What I didn't tell you is that, see, amplitude scintillations can cause deep fades in the signal strength. So you lose the signal. Phase scintillations, when they become very rapid, the frequency lock is lost. Phase lock loop doesn't work. When the satellite rises above the horizon, the GPS and all, your receiver locks on to that. So that lock is lost. So there are actually, but there are, if you look at the phase data, is really compromised because you suddenly see gaps because it has lost lock.
Okay, fine. Thank you.
hypothetical questions.
Yeah, sure.
The magnetic field, that is the pole, recently we saw that it is getting shifted in very slow time scale.
Yes, yes. Not so slow also. Over.
So how it will influence all the plasma bubble formations theories?
Plasma bubble is not, you know, change so much, but storm effects can. Yeah, one thing, you know, the way it can change is because if the pole drifts, you know, then your storm time patterns of currents in the high latitudes also shifts. Okay, because that is very much decided by the location of the pole, you know, and if that shifts, these changes in the equatorial region, which I said, you know, because those are due to these currents leaking out. So that will change, you know, even some of the times will change and so on. So it can affect, yes. Because normally, you know, magnetic field models are changed every 5 years. But this time they had to change it in between because of the rapid. And something I didn't know earlier, but in airports, all the runways are marked with the magnetic lat long. So if that changes, so in the northern and, you know, near the poles, they have to change on that.
Madam, this declination line which passes through Ahmedabad and it crosses through MP and passes through 0-degree declination line I'm talking about. It passes through Nepal and all. And we have in the north plus 2.5, in the south around minus 2.5. Are we mapping this in Indian Institute of Geomagnetism?
No,
I mean, in
what
India we
is
have.
it that passes?
Actually, in India we have a declination factor ranging from top to bottom, deviating by just plus and minus 2.5 degrees, something like that.
So what factor?
Declination factor.
What is declination factor? Declination is the angle between.
Yes, ma'am. Angle deviation.
Yeah. Yeah, that changes, but yeah.
My question is, like in Ahmedabad, this line, 0-degree line passes through Ahmedabad, through our central India and passes through Nepal.
Yeah.
In the northern side, we are having a deviation of around 2.5 degrees.
Yeah.
And in the southern coast, I mean, we have around minus 2.5 degrees.
Yeah.
So are we mapping it, or I generally see that data from US only. US का तो बहुत खराब है, क्योंकि US में तो.
नहीं, US में नहीं, South America में. There the declination is really, you know, I mean, you can see the magnetic field lines are very different, they inclined to.
The number deviates by more than 10 degrees and.
Yeah. So here there will be some slight difference between the occurrence pattern, seasonal occurrence pattern of plasma bubbles, but it will be unobservable probably. Whereas South America, it's very clear.
I'm curious about your comments about the GPS. Is GPS generally more accurate during the day versus night, or there's not much of a difference?
No, generally it's more accurate
during
at
the
night because daytime the ionosphere is stronger. There is more plasma density in the ionosphere because the sun is there producing, ionizing the upper atmosphere constantly. So recombination is there, but the production is much higher than recombination. So the plasma density, you know, keeps on increasing. Then after sunset, recombination starts taking over because there's no production. So the plasma density decreases. And once the plasma density decreases, you know, you have less ionosphere to bother about. So the GPS is in general more accurate during the nighttime than.
So when you were talking about the spatio-temporal separation of the data, I was wondering if you looked at the phases of the moon as a vector to separate the data and if it makes any difference or not.
You know, as I was saying, there are atmospheric tides which give rise to the electric fields in the low latitude and equatorial ionosphere. Okay. Now, the atmosphere has two contributions, one from solar heating and the other from lunar gravitational pull as in oceans. That depends on the phase of the moon. So there can be small shifts in the electric field. And there are things, there is, for instance, there's something called sudden stratospheric warming, which takes place actually in the high latitudes, but its effects are felt even in the equatorial. We live in such an interconnected, if you work in a field like mine, you realize how interconnected we are. So sometimes the high latitude things do come down to the low latitude. Even this thermospheric, that happens in the neutral atmosphere, but ultimately it affects the ionized part of the atmosphere. And that, there, as you were saying, that phases of the moon has been found to be important, because some, when you have a disturbance in the thermosphere coming in from sun, and it interacts with the tides, it depends on the nature of the tides here. So that, if it depends on the lunar phase, so that interaction will also be different. So actually people have found, the different phases of the moon, the effect of the sudden stratospheric warming depends on the phase of the moon.
Thank you.
Any more questions? If there is no questions, then let's have a big hand to before I conclude, I have to do a few more things. I request Dr. Sundaram and Dr. Venkat to hand over a small memento to the speaker. Please come.
Yeah, it's been a particular honor for me to have these two present here. Thank you so much. Thank you very much. Yes, it is all very practical. Sure. Thank you.
And I request Professor Sain to hand over the small memento to the family members.
Okay, yeah. Yeah. Thank you.
I just want to say one thing. That it has a comic book on plasma. Our former outreach division head, that was his brainchild, because nowadays kids are more familiar with the comic book. So that's the introduction of the plasma. And it has been translated on almost 20 languages? Yes. 20 languages. Especially designed for the kids.
Obviously, Dr. Sen helped giving for the conference series, but really, Paritoshji is the main one organizing everything and making it happen. So please give him a big hand.
Lastly, thanks to the outreach division for all this YouTube online facilities they have provided. And this lecture is available in the YouTube also. If you type 4th A.K. Sundaram lecture, then you'll find this in the YouTube. Thank you. Thank you once again, all of you, for attending this lecture.